Hi everyone, we are now moving on to the last part of magnetism. It is 5.4 and it's the right-hand rule. So how do you get a magnetic force using the right-hand rule? And we're going to be applying it to particles and wires and rings and everything that we've learned before. Okay, if you haven't done it, please go and do the readings. Coletta chapters 21 and 22. This is related to homework 6, Magnetism in Physics 112, homework 8, Magnetism in Physics 131. So essentially this is what electromagnets are, right? You have a coil of wire, you have a magnet, and they will either create a force on the other object or, one will be creating a force on the other one. So when you increase the strength of the current, that will increase the strength of the magnetic field. If you increase the magnet itself, making it a more dense magnet, increasing the dipoles of the iron core, it'll also increase the strength of the electromagnet. Okay. You've seen these things again. Yeah, this is related to this magnetic force can be applied to levitate an object, right? So you see like a little, zoom in here, a little cube floating above a superconductor, right? So this magnetic force is applied to a lot of stuff. It's applied to power generation. It's applied to transportation. It's applied to speakers. It's applied to everything. So what is a magnetic force? So how does an interaction between a current and a magnet create a force? And what are the rules and how do you quantify it? All right. Well, here's a picture, and let's make sure. You have a picture of an electron beam. The electrons are moving to the right, and so the electrons are moving to the right. They enter a region of a magnetic field, and this interaction of the electron's magnetic field and the magnetic field due to the magnet itself, that interaction of magnetic fields actually creates a force. And you've seen that in magnets before, right? You have a north and north, and you apply those two magnets to each other. Well, those two magnetic fields are interacting with each other, and a magnetic force arrives, comes out of that. Well, this is the same concept of attraction and repulsion of two magnets. It's just with a current carrying wire, which creates a magnetic field, and also a magnetic field created by a magnet, right? So there is a relationship between this, and it is a cross-product relationship, right? So if you have a charge that is standing still, right here, a charge that is standing still is not going to create a magnetic field, okay? So if you have a magnetic field and you have a charge that's not moving and it's embedded in that magnetic field, that charge is not going to begin to move. It's just going to sit there. So there's not going to be a relationship. There's not going to be a force created out of that relationship. However, if you do have a moving charge embedded in a magnetic field, if those are both parallel, meaning the charge is moving in the same direction as the magnetic field or opposite the direction of that magnetic field, also a force will not be created. That magnetic field is not going to push on that charge at all. But what you find out way over here is if you have a magnetic field pointed up the screen, up the plane right here, and you have a charge, positive charges moving to the right, well, that is going to create an orthogonal force, which is going to be perpendicular to both of those guys. So when the charge's motion is perpendicular to the magnetic field, a now a third dimension force is created due to the interaction of those two magnetic fields. And so that's what these two are representing. That if the closer that velocity, direction of that velocity is closer to that perpendicular between the force and the magnetic field, creates a larger and larger force. So that's what that's representing. So this is actually going to be related. There's actually a way to predict that using your right-hand rule, and we're going to quantify that. So essentially, particles moving perpendicular to the direction of the magnetic field lines are going to experience the greatest amount of force. A particle that is moving somewhat perpendicular to that magnetic field is going to experience a little bit of a force, and a particle that is moving parallel to that magnetic field is going to experience no magnetic force at all. And that's essentially what this earlier slide was representing. Okay? So this is called the right-hand rule. Okay? So you point your thumb, as always, in the direction of the particle, the positive particle is moving, or the current. Okay? Your finger, your index finger, is representing the direction of the magnetic field. So the magnetic field line's pointed up, or point your thumb in the direction that north is pointed. That is the direction of the magnetic field. Okay? And then your middle finger, this middle finger kind of popping up, or I like to keep my hand open, and the direction that my palm is pointed is the direction of the force, of the magnetic force. So for example, if you have a positive particle moving to the right through a magnetic field pointed up the plane, it will experience a force applied in this direction. Notice how it reflects exactly what's happening here. And so the magnetic force on a particle is going to be Q times V, so it's the particle sign times its velocity vector, cross B. And that cross product ends up being a sine of theta, where theta would be the perpendicular right here. Alpha, I should say. Alpha is the angle between the velocity vector and the B field vector. Okay? And that's what it represents right here. And that magnetic field force is still just in newtons. Charge is in its unit is coulombs. Velocity, its units is meters per second. The B field's unit is teslas, and alpha is the angle. All right. So there's a little idea of flux, right? So if you're in physics, if you're in the physics courses in the next section, we'll get it more into magnetic flux. But essentially, the velocity vector is the angle between the magnetic flux, or the magnetic field lines, and the velocity vector is what is going to be that sine of theta. That theta is the angle in between those two vectors. Okay? So I had said that you have to point your thumb in the direction that the positive particle is moving. Okay? Or the current is pointed. Well, you'll notice I said positive particle or current. So when you do the right-hand rule with a negative particle, and you're pointing your index fingers in the direction of the magnetic field, and your thumb in the direction of the velocity vector. Whatever direction that your index finger points, the force is going to be opposite that direction. So if you have a negative particle, do the right-hand rule, and whatever your hands tell you, do the opposite of that. And I kind of like to think that negative particles like to lie. I don't know if they like to lie. I've never really met a negative particle, but one thing for sure, that this is predictive of a positive particle or a current. That means you have to do the opposite when it's applied to a negative particle. So please still use your right hand, because it's the right hand rule. Just do the opposite. Please don't use your left hand. Okay? Well, let's practice this. Let's see if we could practice figuring out the direction of the force, and then in a little bit after we practice this, we're going to try quantifying it. So what we have is we have a positive particle entering and moving to the right, entering in a region of space where a magnetic field is pointed up the page. All right. As it is moving in this magnetic field, what direction will the magnetic force be applied? Will the magnetic force be pointed to the left, pointed right, pointed down, pointed up, pointed into the page, pointed out of the page, or will no magnetic force come out of this? So go ahead and pause the video and try to figure this out, okay? So what you're going to do is you're going to point your thumb to the right. So your hand should be, your thumb should be pointed to the right. You're going to keep your hands open, and you're going to make that triangle with your fingers. Now, you have to keep a 90-degree angle between your thumb, your index finger, and your middle finger. So my thumb is pointing up, and my index finger is pointed up my screen. So my thumb is pointed to the right, my index finger is pointed up the screen, and my middle finger should be pointed right at my face. Okay. Another way of doing this is you leave your palm open, actually. Point your thumb to the right-hand side of the screen. All of your fingers should be pointed up the screen, and you should be looking straight at your own palm. That means the magnetic force should be coming straight out of the page. Okay? And I will mark that. Come on. There we go. It should be pointing out of the page. All right? Well, let's do this again. Let's do this problem, but for a negative particle. So a negative particle is now moving to the right. The magnetic field is pointed up the page, and I want you to figure out the direction of the magnetic field applied to this negative particle. So go ahead and pause the screen, apply the right-hand rule, and go ahead and figure this out. Pause now, please. Okay, so I'm going to, again, point my thumb to the right, and my fingers are pointed to the top of the screen. So again, I'm looking at my palm. But again, from what we learned earlier, the right hand is predictive for the direction of a positive particle or the current. Okay. A negative particle, you do the opposite of whatever your hand is telling you to do. So since my palm is pointed at my face and this is out of the page, that's what the direction of the force would be for a positive particle. A negative particle will be into the page. So the answer is E. All right. Let's try another one. A positive particle is moving down the screen. And it's going to be entering a region of space where there's a magnet pointed where north is labeled and south is labeled. So try to figure out the direction of the magnetic force in this situation. Will it be pointed left, right, up, down, in, or out of the page? Or will it be zero? So go ahead and pause the screen and try this out. Right. You've unpaused the screen. Unpause the video. So my thumb should be pointed down the page. Okay, so I have to kind of angle my hand. Okay. My thumb is pointed down the screen. My fingers are pointed to the right. And I'm keeping a 90-degree angle in between my thumb and my fingers. And my palm is facing my face. So this, again, is actually going to be out of the page. Wow, a lot of them are out of the page. My point is, this region of space, this magnetic field is going to create a this magnet is going to create a magnetic field to the right. Okay. And when it comes into this region of space, it's going to begin flying up towards your face. A force is going to be applied that's going to redirect it towards your face. Okay? Let's try another one, and this one is going to be in 3 dimensions, so we're going to have to figure this out. So we're going to have to be pointing our fingers or palm or thumb in or out of the page. So We have a positive particle entering a region of space listed below. So the positive particle is moving up, and the magnetic field is pointed into the page. What is the direction of the magnetic force? Okay, is it going to be pointed left, right, up, down, into the page, out of the page, or zero? So go ahead and try this one. All right, if you've tried this, you point your thumb, keep your hand, your palm open, and you're going to keep your thumb, it's almost like you're shaking somebody's hand. You're going to keep your thumb at a perpendicular angle to your fingers. So your thumb should be pointed up the page, up the screen, to the top of the screen. Your fingers should be pointed into the screen, kind of like you're shaking somebody's hand. And if you notice, your palm should be pointed to the left side of the screen. That means when this positive particle begins entering the region of space, it's going to be moving up, and then that magnetic field is going to begin turning it to the left. So the answer is A. Let's try another one. Now this positive particle is moving to the right, and again the magnetic field is still pointed into the page. So go ahead and pause the video and try this one out. Okay, so you've unpaused the video. You're going to point your thumb to the right of the screen. Your fingers should be pointed into your screen, and it should be almost like you're holding up hors d'oeuvres or something, or a plate, holding a plate on your hand. Okay, so your palm should be pointed to the top of the screen while your fingers are pointed into the screen, and your thumb is pointed to the right hand side of your screen. So the magnetic force should be pointed up. So that's pretty easy, predicting the direction of the magnetic force. Now let's try something a little bit different. Now you're going to be given the direction of the particle's velocity and the force. And you have to figure the direction of the magnetic field that would be causing this force. So this negative particle is going to be entering a region of space caused by a magnetic field. When it does, it starts experiencing, so this negative particle is moving down, and it starts experiencing magnetic force to the left side of your page, your screen. What is the direction of the magnetic field that would be causing this magnetic force on this negative particle? All right, would it be left, right, up, down, in, out, or zero? Pause the video and try it out. Try applying the right-hand rule. Don't forget this is a negative particle. All right, so you've unpaused the video. Even though this is a negative particle, you're still going to apply the right-hand rule. I'm going to point my thumb down the page. Okay, I'm pointing my thumb down the page, and I'm going to angle my hand so that the force, my palm, while my thumb is being stilled to the bottom of the page, my palm is going to be pointed to the left side of the screen. And right now, my fingers are pointed at my own face, out of the page. But since this is a negative particle, it's going to be into the page, right? If this were a positive particle, it would be out of the page. But since it's a negative particle, the magnetic field should be pointed into the page, and that would be creating a force to the left of your screen. Okay? Let's try another one. Oop, actually, let's try this line of thinking, line of reasoning with a wire. So what's really cool is that current-carrying wires, a current, again, are moving electrons, and those electrons moving create a magnetic field when they're moving on top of their electric field. But when you put a current-carrying wire in a region of a magnetic field, that wire will actually bend in response. So a force will be acting on that wire due to the other magnetic field it's interacting with, right? And so this is actually a really interesting problem, because you have to kind of think about if you have wires next to each other, well, two wires are going to be creating two magnetic fields, and they're going to be pushing on each other all the time. So forces are magnetic forces are going to be applied to everything with a current carrying wire within a close enough region to another one, or a magnetic field. So just like before, how do you quantify this? Well, it's quantified by the current times the length of the wire. And so it's really actually the length of the wire times the current, and I should probably write down what I'm talking about. Length of the wire, and it's going to be I cross B, right? And you have to, so this is the length of the wire in meters, this is the current in amps, and this is the magnetic field in Tesla, right? Well, that I cross B ends up working out because they have to be at 90-degree angles to each other. And it ends up working out to be the sine of theta, right? And so you could rewrite this formula LIB sine of theta to ILB sine of theta, right? What does that mean? Well, that means that when the magnetic field is pointed into the page, a force, and the current is pointed up the page, a force is going to be created. So this right here, this angle in between the current and the force is that angle theta. Okay, so that force vector, oh God, I'm so sorry. That is not true. It's the angle in between the magnetic field vector. So the magnetic field is into the page. Let me zoom in on this. Magnetic field is into the page. And the current is pointed up the page. When the current is pointed up the page, that angle between theta, between the current and the magnetic field, is theta, right? And that gives rise to a force. So this is a current carrying wire in a magnetic field and a force. That magnetic field then creates a force on that current carrying wire. And so again, just like with a positive particle, you point your thumb in the direction of the positive particle, and in this case the current. Your index fingers or your fingers could be pointed in the direction of the magnetic field, and a force's direction of your palm, or if you do it this way, the middle of your finger, the middle finger. Okay? Well, just like last time, let's practice this. Let's practice the right-hand rule. A good strategy, again, there's strategies to doing everything, is basically make sure you note the direction of, you apply the right-hand rule, okay? So paying attention to the source of the magnetic field. It could be an actual magnetic field itself. In that case, they would just give you a B field, or if it's a current carrying wire. Also note what is interacting in that magnetic field. Is it a charge or a wire? And also what kind of charge? Is it a positive or negative charge, right? So a lot of the problems you're gonna have to apply the right-hand rule to figure out the direction of the magnetic field. And just like you've done before, you're gonna then have to create you're possibly gonna have to create a force diagram, right? So once you apply the right-hand rule, that is now your force, and then there might be a force diagram that you have to then do as well. Okay, so you're going to have to use your right-hand rule to figure out the direction of that force vector, which may or may not lead into a force diagram. Well, let's go ahead and apply it to this situation. So you have a battery, and you have a wire right here, and they're both sitting on a table, and you're above the table looking down at it. There's a magnet in case number 1, which is the north is indicated and the south is indicated. So in magnet 1, I want you to figure out what direction the wire would deflect. Would it be up, down, left, right, in or out, or not deflect at all? Okay. Go ahead and pause the video and figure out the directions that each one of these would deflect Actually, let's just do number 1. Let's just figure out the direction that number 1 would deflect, and we'll talk about it, and then you try 2, 3, and 4. All right. So what I'm going to do is I'm going to draw the direction of the current. So to practice what we just learned from the strategies, you have a battery creating a current, okay, and it's going to be creating a current pointed up right here, okay. So the current is going to be up the page. So that's going to be the direction of your palm, of your thumb, I mean. Well, now you have a magnetic field that is going to be pointed to the left-hand side of the page. Okay, so the magnet will create a leftward pointed magnet where north is on the left side of the magnet. That'll be pointed, creating a magnetic field pointing to the left. So now you have a current in a magnetic field pointed to your left. So now I'm going to apply the right hand rule. My thumb is pointed up the page. My fingers are pointed to the left hand side of the page, while my thumb is at a 90-degree angle to them. And I'm staring right at my palm. So this is going to create a magnetic force that is out of the page. All right. What I want you to do is I want you to try that with 2, 3, and 4, and let's see what you get. Okay? All right, let's try it again. Let's try it with 2, 3, and 4. Again, if this is a battery, it's going to create a counterclockwise current. So the current is going to be, again, still pointed up the page, but now it's embedded in a rightward pointed magnetic field. Okay? Put little hats on everything. And when I do that, my thumb is pointed up the page to the top of the screen. My fingers, my hand is extended out. My fingers are pointed to the right-hand side of the screen, and my palm is facing into the screen. So that means there's going to be a magnetic force into the page. How'd you do? Why don't you try number 3? Okay. Number 3, you have a battery creating a current, so that's going to be creating, in this case, since the battery's been reoriented, the current is going to be moving clockwise, so that means at this point it's going to be moving down the page. And again, this battery is pointed, this magnet is pointed to the left. Okay. So now I'm going to point my thumb down the screen, and I'm going to point my index fingers to the left of the screen. So that means my palm is going to be pointed into the screen. My fingers are pointed to the left of the screen. Simultaneously, my thumb is pointed down the screen. My palm is pointed into the screen. So that means the magnetic force is into the page. Number 4, the current is still moving down, but this case, the magnetic field is pointed to the right of the page. And when that's done, that case, I get my palm pointed out of the page. Okay. So if there's any questions, then please talk to each other. Please interact with each other. All right. This is a good practice problem. So again, in number 4, my thumb is pointed down the page. My index fingers are pointing to the right-hand side of the screen, and my palm is kind of facing out of the screen. Well, now that we've practiced that, let's go ahead and try it. So here we have a length of wire that is 10 centimeters long. So this thing is 10 centimeters long, which is 0.1 meter long. Okay, and it carries a current of 3 amps. And the wire is in a magnetic field that is 2 Tesla into the page. And so what you're supposed to do is figure out the direction and also magnitude of the force acting on this wire. All right. So here's the equation that we've done before. So what we had learned before is IL cross B is ILB sine of theta. Okay. In this case, theta is going to be 90 degrees. Because it looks like the current and the magnetic field are pointed in at perpendiculars to each other. So that's going to be 90 degrees. And so since those are at a 90-degree angle, the current and the magnetic field are at a 90-degree angle, the sine of 90 degrees is just going to be 1. So in this case, it's actually a really easy calculation. The current is 3 amps. The length of wire is 0.1 meters. And then the B field is 2 Tesla. So this is going to work out to be, what is that? 3 times 2, what is that, 6? 0.6 newtons. So this is going to be 0.6 newtons. So now we know the magnitude of the force. Now we have to figure out the direction of that force. Well, let's apply the right-hand rule. You're going to point your thumb up in the direction of the current, so your thumb should be pointed to the top of the page. Your index fingers should be pointed into your screen, and your palm should be pointed to the left of your screen. So that means a magnetic force should be pointed to the left. So that is the direction of the magnetic force. Okay? So now we know it's going to be 0.6 newtons to the left. It's also known as the negative I direction as well. You might have some books that give things in the I hats. So this would be in the negative I hat. The negative I direction as well. And you put a little hat on that guy. Anyways, so that's how you kind of quantify. So it's a pretty easy little problem. Well, let's practice more with the right-hand rule. Okay, so now let's do some other things. What do you do when you have a charge interacting with a current? Okay, so now we're going to get into you're not given a magnetic field, and you have to figure out the direction of the magnetic field. And so in this case, you have a current-carrying wire that is pointed up, and you have a charge, a positive particle that is moving out the page. And what's going to happen to the direction of this motion of this charge? Okay, will this charge be pushed out of the page, into the page, in the positive X direction, in the negative X direction, or in the negative Y direction due to this current carrying wire? So go ahead and pause the video and see if you could apply the right-hand rule with the curl of the thumb around a current carrying wire, creating a magnetic field. And then after you do that, embed your positive particle in that magnetic field using the right-hand rule to figure out the direction that of the force, the magnetic force on that positive charge. So pause the video now. All right, so you've unpaused the video. This current carrying wire is creating little loops around it. Okay, and I'm pointing my thumb up the page and I'm curling my hand, and it looks like it's curling this way in little loops out of the page and then back into the page. So it looks like on the right hand side of this wire you're going to have a magnetic field into the page, and so that means by symmetry the other side of the page is going to have a magnetic field out of the page. Okay, well, this charge is moving up the page now, and is moving into a region of space where the magnetic field is pointed out of the page. So I'm going to point my thumb in the direction that the positive charge is moving. My index fingers are pointed out of the page towards my own face, okay, and my palm is pointed to the right side of the screen. So this magnetic field is going to be pointed to the right hand side. So a magnetic force is going to be created to the right hand side of the screen in the positive X direction. Okay? So that's how you do a problem where you have a magnetic field created by a current carrying wire. And if you remember Ampere's law, over 2 pi d, right? So the magnetic field at this point right here, where this charge is right there, that's the magnetic field right here. Okay, so the magnetic field at where the charge's location is, so this distance here is the distance d. Okay, and then what you do is you apply that QV cross B, which is going to be QVB sine of theta, which is sine of 90 degrees. So that's going to be 1. So this is going to be QV, and that B is going to be the mu naught I over 2 pi d. So that's how you would calculate it too. So that's how you'd quantify the magnetic field. You have to then start to combine the magnetic field created by a current acting on, so this is the magnetic field created by the current at this point right here where the red dot is, a distance d away from the wire. Okay, so that's that d distance, right? And this is QV cross B. So that's Q, and we should probably put absolute values around all that stuff. So that's what you do. And the direction of that force is going to be to the right. So this is how you would quantify that. Okay? So now we're kind of getting into a section where you're going to have to start figuring out the direction and also magnitude of a magnetic field due to a current carrying wire or a charged particle, and then apply the magnetic force and that'll give you the magnetic field, and then you apply it to the magnetic force to whatever other particle it's acting on, either a particle or a wire. Okay? It looks like we were right. Another situation that you have to think about is when you have two interacting wires. You have two wires, right? So this current right here, this bottom wire is creating a current to the right, and when you do that, this bottom wire is going to be creating a magnetic field out of the page around the top wire. Okay, so now the top wire has a current out of the page, so you apply the right hand rule. My thumb is pointing to the right. The magnetic field right here is caused, so this is the B field around this wire is due to the lower wire, so wire number 2 is creating a magnetic field out of the page around wire number 1. So I'm pointing my thumb to the right hand side of the page, my index fingers are pointing at my face, and I get a magnetic force pointed down. Okay. When these two currents are pointed opposite, right? Correct. So now the index and forces are equal and opposite, so these two wires would come together, right? So current number 2 now is pointed to the left, and current number 1 is pointed to the right. So now if I point my thumb in the direction of current number 2, and I curl my fingers around, right? So I'm going to be curling, this is creating a magnetic field, and over here it's going to be the B field in this situation is going to be pointing into the page. And so around wire number 1, you're going to have a magnetic field pointed into the page. Well, now I'm going to point my thumb in the direction of current number 1 right here. So, and I'm pointing my index fingers into my screen. So now my palm is pointed to the top of my page. So that means that force is going to be pointed up, and forces are equal and opposite, so current wire number 1 is going to be pushing wire number 2 down. So they're going to repel. And so you get this type of, so here's how to quantify that. But really what it is how they got that is the B field due to a current carrying wire is this, 2 pi d, so that's Ampere's law. Okay. And so the magnetic field of a wire is going to be IL cross B, or IL B sine of theta, but that'll sine of 90 degrees is going to be just 1, right? So this is just going to be 1. So this is just IL B, which is going to be which this is going to then be just IL, and B is going to be mu naught. So I'll just call this wire number 1 is experiencing a force on it due to the magnetic field from wire number 2. So that wire number 2 is caused by current 2. So this is going to be current number 1 times the length times the magnetic field caused around it by wire number 2, which is going to be mu naught I2 over 2 pi times the distance apart of those two guys. And so that's how they got this right here. Okay? So let's go ahead and apply it. Well, we have 2 wires that are a distance r apart, and r is going to be 0.0045 meters apart. And they're 2 wires of equal currents but in different directions. And we know the length of each wire is a distance L. Okay? All right, and they didn't give us, they didn't give us the length of the wire. Can't figure this out without that length of that wire. So I'm going to go ahead and give us this wire. This is a problem I made up, so I wish I'm going to say this length is going to be, let's say it's going to be 0.2 meters or 20 centimeters. Okay? So here we go. So let's figure this out. You're supposed to figure out if these 2 wires are going to attract or repel, and you're supposed to figure out the magnetic force, the force of that magnetic force. So go ahead and pause the video and try this out. Okay. Well, wire prime, which actually, I'm going to do this. I'm going to call this blue. You're my boy, blue. This is wire number 1. And wire number 1, let's figure out the direction of the magnetic field it's creating. Well, wire number 1 is the current's pointed to the right, so it's going to have loops in and out of the page. So it looks like wire number 1 is going to be creating a magnetic field everywhere outside itself. And let me do this. It's going to create a magnetic field down here into the page. Well, everywhere above it, wire number 1 is going to create a magnetic field, and this is in. wire number 1 is going to create a magnetic field around wire number 2, and wire number 2 is going to be red, and I'll mark that in a second. So this is going to be the magnetic field due to wire number 1, which is going to end up being out of the page. So it's going to be a positive magnetic field, right? And so wire number 2, I'm going to now mark as red, is now embedded in that magnetic field. Incidentally, wire number 2 is making a magnetic field around wire number 1 into the page. And I'm marking that here. So it's going to be negative. And it's also going to create a magnetic field on the top part of it out of the page too. But that can't, that's not really doing anything. We're just going to apply, we're just going to look at how, you have to pick one wire to analyze, right? So let's go with wire number 2 is embedded in wire number 1's magnetic field. So blue around the red wire. Okay? Well, let's go ahead and do the math. Okay? And let's figure this out. Let's apply the right-hand rule. So when we apply the right-hand rule, you have a leftward pointed current from I2 pointed to the left, and I have an outward pointed magnetic field, which is the blue field around it. That's going to create a magnetic force pointed up. And since forces are equal and opposite, that means wire number 1 is going to experience a magnetic force, that same magnetic force, down. Right? If we do the right-hand rule of this guy here, you're going to point your thumb to the right part of the page, point your index fingers to inside the page, index fingers okay, let me see. So point your index fingers. Anyways, this is going to experience force down. Okay. So we know that these two wires are going to repel. Well, let's figure some things out about that. So wire number 1's magnetic field around it, around wire number 2, is going to be equal to mu naught times wire 1's. So this magnetic field is what we're figuring out. That's going to be equal to mu. The magnetic field there is going to be equal to mu naught I over 2 pi, and they are distance r apart. Okay. And so once we have that, now what we could do is embed this. So let's figure out, so now we know the magnetic force is going to be equal to IL cross B. So the magnetic force on wire number 2, and I will use red for that, and so wire number 2, we're figuring out the force on wire number 2, which is this guy right here, which will be up, which now is going to be due to wire number 1, wire number 1's magnetic field, and I'm going to use blue for that. And that is due to B1, wire number 1's magnetic field. So let's go ahead and try it. So we have I2 times the length, which is going to be 2 meters, and then the B1 magnetic field, which is going to be mu naught I1 over 2 pi r. So I'm going to rearrange this formula so that it looks nice and clean, which is going to be equal to mu naught L I1 I2 over 2 pi r. Okay, and then I'm going to now plug in our numbers. So mu naught is going to be 4 pi times 10 to the negative 7th, and that's Tesla meters per amp, and it's going to be multiplied by, this is a pi, times the length, which is 0.2 meters, times current, each current, which is 15,000, so this is 15,000 amps, times 15,000 amps, that's going to be huge, divided by 2 pi, and let me go ahead and center that 2 pi, whoops, trying to erase. So this will be 2 pi times the distance d apart. Whoops. The distance d apart is, or distance r apart rather, is 0.0045 meters. Okay, so I'm going to multiply all that together. Just simplify 2 pi, 4 pi divided by 2 pi is just 2 times 10 to the negative 7th, right? So I'm going to plug this all into my calculator. So I'm going to go 2 times 15,000 times 15,000, oh boy, times 0.2 equals, and then I'm going to divide that by 0.0045. So that is a huge number. But I didn't apply 10 to the negative 7th. So I'm going to apply that now. 1, 2, 3, 4, 5, 6, 7. So this is going to experience a force of, looks like 20,000 newtons. Good Lord. That is a huge force. And that's a lot of amperage, by the way. It's not a normal amount, but that's something akin to what a power plant would produce. So anyways, so that's how you apply force due to current carrying wires. Well, let's practice this. The hardest part is not really much the mathematics. That's pretty simple. It's applying the right-hand rule. So you're going to have to practice the right-hand rule. But we kind of did it here. And if you'll notice, currents pointing in the same direction, they will attract. Currents pointing opposite directions, they will repel, but we use the right-hand rule. Current number 2 is creating a magnetic field around the other wire. And then so now you embed that wire in that magnetic field, and that's how you get that force. Okay? So now let's move on to something that's really cool, is you can what is basically a mass spectrometer, okay? So I skipped ahead a few slides, but here we go. When you put a magnetic field, if you have a charged particle that's moving along, minding its own business, so I'm going to draw this. So you have a charged particle moving along, it gets injected into a magnetic field. And here's the interesting thing about this. So this positive particle gets pushed into, it's given a velocity to the right, and it's being pushed into this magnetic field. Okay, and that magnetic field is going to be pointed out of the page. Well, it's going to then create a downward force. So I'm applying the right-hand rule. My thumb is pointing to the right. My index fingers are pointed out of the page at my own face. So now my palm is pointed down. Now, that means it's going to create a magnetic force down. Well, that's going to cause the particle to start to get to right here. And then at this point, this guy is going to start moving down the page, okay? And it's going to cause a velocity down. And that velocity down, I'm still, now my thumb is pointed down the page, my index fingers are pointed out of the page, and that's going to create a force into the page, right? So now we're kind of getting into centripetal force, or center-seeking force. So here's the weird part. So when it gets injected into this, what happens as it can, let's say you had a rightward, so you'll notice it starts to turn in a circle. Well, what would happen if you injected this particle into a rightward pointed magnetic field? Well, now you get the motion of the particle starts to do this, and this starts to look like a helix. Okay, so this particle starts to get kind of look like a wound up spring, which is, it's also called a helix, and it creates these little small loops, so it starts to vary the trajectory. Well, that force, that centripetal force that's causing this helix, so this is looking straight at the helix, and this thing's curling around, coming at your face, right? Well, a mass spectrometer, what you do is you just inject, you have a little window, and you shoot a particle out this way, and you have an inward pointed magnetic field, and what it does, it comes around, and it ends up taking a path like this and hitting a wall. And I'll show it to you in the next one. Well, what's happening is that magnetic field is causing a force that is a center-seeking force, which is mv squared over r, right? So now the magnetic force is qv cross b, and that qv cross b is equal to mv squared over r. So now you could actually predict the radius of this circle that it's taking, this path of this circle that it's taking, by solving for, you just take this part and solve for r, which is going to be mv over qb. And now, using frequencies, you could apply 1 over the period, which is velocity over 2 pi r, which is it's the total distance of a full circumference, okay, where r is going to be this part. And now you could actually predict the frequency of a particle moving around in a circle from a mass spectrometer, but also with this r here, you could actually predict the path that it takes. So here is a model of a mass spectrometer. Notice that you're shooting particles out this way, and when they enter this region in of the magnetic field, okay, they're going to start taking a circle. Particles that have more charge on them, okay, that have more charge on them, okay, so let's go back to this. If this particle has more charge on it, so this has a huge charge on it, actually let's go to this one. Let's say the particle has a huge amount of charge on it. Well, charge and radius are going to be inversely proportional, right? And so I'll copy this equation over here. R is equal to mv over q b. So here's the wonderful part about this. You could not only predict the mass of the particle, but you could predict the charge of it too. So if you have a hugely charged particle, you don't know the charge of the particle, you know its mass, you know its velocity, you know its magnetic field. Well, if it takes there's a whole bunch of little sensors built up right along here. And depending on what path it takes, let's say it takes a longer path, like this long one, that means that charge is going to be a huge charge, okay? And that means it's going to take a smaller path, right? So what's interesting is the larger charge objects, charges that are huge, like a big old Q, are going to take a shorter path. They're really going to react to that magnetic field. But a smaller charge is going to end up way out here and take a longer path. It's going to have a longer radius, right? Another cool thing, if all these particles are being injected at the same speed and they're experiencing the same magnetic field, you could actually figure out the mass of the particle, right? So if the particle has a huge mass too, if its mass goes up, well, mass is directly proportional to radius. So that means a heavy mass is going to have a hard time turning. So a heavy mass object will also land in these lower detectors, and a smaller mass will end up in these detectors closer to the center of the circle. Okay, so that's how we could actually use a mass spectrometer to not only figure out the charge of the particle, but also the well, how much of a charge of the particle it is. I didn't write this. Negative particles would do the opposite of this. They would take this path. They would do an opposite path, right? Positive particles would, let me see. I might have gotten that backwards. Let me think. Actually, this is going to be the negative particles here on the bottom. Negative particles are going to take this path. Positive particles, positive Qs are going to take this path up here. Up there. So anyways, you could actually figure out not only the charge of the particle, whether it's positive or negative, but you could also figure out the magnitude of the charge and also the mass of the object, as long as you're keeping the velocity and the B field constant. So it's pretty neat. So that's how a mass spectrometer works. Well, that finishes up magnetism, and I hope you enjoyed it. This is a really cool thing, and we're going to use magnetism to build on how inductance is created and how you actually create a generator and all that kind of stuff. So it's really neat. Have a good day.